Welcome again to the new lecture of the course Properties of Materials. So, let us just briefly recap what we did in the last lecture before we move on to the contents of this lecture. So, in the last lecture we looked at the stress that is required to operate a Frank-Read source, and we saw that this stress is equal to 2 GB divided by L, where G is the shear modulus, B the Burgess vector, and L is the length between the two pinning sides. So, if you have, this is the dislocation, this is L, these are the points A and B, and when you move the dislocation it goes in this fashion, and then finally it comes like this full circle, and this is where annihilation. So, it leaves basically a loop like this, and this segment goes back to its own state. So, this leads to basically you can say dislocation, creation, and you can say multiplication. So, basically increase in dislocation density, and we also saw that this stress is proportional to square root of rho, which is rho is dislocation density. So, more the dislocations in the materials are, more is the strength, and this mode of strength is called as strain hardening. So, basically what happens is that as you deform the material more and more, so this is, let us say, the deformation, let us say you go up to this point, then you come back to this point, again you start the deformation, you will go back to this point, and then you again start, and let us say if you want to come back to this point again. So, we make the, so this is sigma, this is E, so this is first pass, you come back again start, then it comes back, then let us say you come back again, recover the elastic strain, maintain the, and then again you increase the, so of course I am not considering the strain rate kind of thing here, but then again, so this is how the yield strength keep increasing. So, this is the yield strength to begin with. So, it has gone from here to here to here, but what happens is that in reality as you keep deforming the materials also become stronger, but they also become less ductile. So, if your first pass shows a behavior like, so let us say the first deformation is like this, you do not deform it, you do not let us say break it, the next one will lead to yield stress which is like this, and the third one as you make stronger it will lead to like this. So, so basically you can say the materials become stronger. So, this is sigma, this is E, and this is increasing percentage deformation. So, as you increase the percentage deformation with percentage deformation, so as percentage deformation increases, sigma y increases, but E decreases, the overall strain decreases, the plastic strain decreases. So, that is something which you have to keep in mind. So, now let us see, so we will come back to this maybe later on, but what is the reason that why is, the question was why does increase in dislocation density lead to increase in strength? And this we said is counterintuitive, because we said that dislocations are weaknesses, they give rise to lower stress. So, why is that when they increase in number they give rise to increase in strength? So, basically what happens is essentially dislocations, when there are too many dislocations, they start interacting with each other. And this interaction causes increase in stress. So, what is this interaction type? So, let us say the first interaction could be, let us say you have this a dislocation like this, all right, and you have another dislocation somewhere here which is let us say, so this is first edge dislocation, this is another edge dislocation. So, these are both two edge dislocation, one edge and two edge. If you look at the stress field around this dislocation, this is compressive, but this is also compressive. This is tensile, but this is also tensile. So, the reason, so when you have two edge dislocations, so if you have two dislocations of same sign close to each other, they repel each other, because the stress fields are similar. So, you have compressive, tensile. When you want to put them together, they do not go close to each other because they start repelling each other because of similar stress fields. As a result, this leads to increase in stress required to cause deformation. So, now that you have so many dislocations in a crystal, the dislocations are bound to come close to each other. Of course, you will have instances when you will have positive and negative. So, if you have positive plus negative, so that is this and that, they will annihilate each other. So, they will make the crystal perfect, and if you have this plus this, they will repel, or if you have this plus this, they will repel. So, basically you can say similar signs repel and opposite signs annihilate. So, this leads to increase in the stress that is required to cause a dislocation, but there are other methods as well. So, imagine for example, if you take HCP crystals. The problem with HCP crystal is, if you look, HCP crystal has only one close packed plane, that is 0 0 0 1, and it has only three directions in this plane. Which are close packed. So, which gives rise to only three close packed slip systems. There are other slip systems as well, the planes which are not necessarily close packed, but the close packed directions lie in those planes, but there is only one slip plane. So, if you have only one slip plane, the dislocation will not, so if a dislocation is there, so if a dislocation is present on this plane, it will not be intersected or interfered by other planes, because there is no, because 0 0 1 planes are basically parallel planes. So, this is HCP structure. So, this is C plane basically, the C planes are all parallel to each other. So, So, as a result, if you have a dislocation here, if you have a dislocation here, if you have a dislocation here, they will not intersect each other. They will be, so there may be instances that they have to be far enough if they are similar signs, and because their stress fields will overlap, but they will not intersect into the path of each other. However, if you take example of BCC and FCC crystals, in BCC you have a slip plane which is 110 type slip plane, sorry 110 plane. So, we can write this as in this fashion. In FCC we have a slip plane of 111 type. Now, if you look at BCC, basically you have, there is a possibility you may have this as a slip plane. So, this is one slip plane. You may have another slip plane which is this slip plane. You may have another slip plane which is basically, you can say this is the slip plane. So, there are multiple slip planes. So, basically some of these slip planes intersect with each other. So, basically you can say slip planes intersect with each other. Same here, in this case also in FCC, if you draw the FCC unit cell, you may have 111 planes intersecting. So, you have, this is one 111 plane, you may have another 111 plane which is like this, you may have another 111 plane which is like this. So, the 111 planes may intersect. So, slip planes will intersect with each other in both FCC as well as in BCC. When they intersect each other, the dislocation motion is not easy, because when it moves one plane, let us say it is moving one plane. So, there is a dislocation. So, there is a plane here. So, let me just go to the next one. So, let us say if it moves in one plane, okay. So, this is the dislocation line which is moving into, it intersects another plane which is, let us say this is another plane, alright. So, it intersects another plane. Now, the moment it encounters another plane, if the Burgess vector of dislocation does not lie in intersecting plane, there is a possibility it might move, but if it moves, it may not move. It may not be able to move in that plane, intersecting plane, because of HKL dot UVW may not be equal to 0. So, that Burgess vector may not lie in that plane. If that happens, because dislocation is nothing but a bunch of atoms. So, bunch of atoms which is basically a faulty region, the faulty region may move from one plane to another, but it may happen that Burgess vector does not lie. If the Burgess vector does not lie, it will not move. So, this will lead to dislocation movement blockage. If that is the case, you will have to increase the stress required to move it to another plane where it finds easy to move. There is a possibility you can also form what we call a sessile dislocation. Sessile dislocation is basically a dislocation which does not move, which is essentially unable to move. So, let us say you have, let us say we have these three vectors, these three Burgess vector, okay. So, one is the red one is the black one and blue one. So, let us say this one is half 1 bar 1 0, this one is half 1 0 bar 1, and this one is half 0 bar 1 1. They all lie on one plane, that is 111 plane. So, the plane is 111 and these are the Burgess vector. Now, it is possible that two of these may give rise to another one. So, if you put them together, half 1 0 bar 1 plus half O bar 1 1, they can give rise to, you can write them as half of 1 bar 1 0. Okay. So, if that happens, then you form a new dislocation, and the energy of a dislocation is given as is proportional to B square. Okay. So, basically it is half GB square, so it is proportional to B square. So, essentially if you look at the energy, the E1, so basically E1 is you can say, if this is A by 2, the A is the lattice parameter, let us say. So, this will become A square divided by 2, E2 will become A square divided by 2, and E3 will become A square divided by 2. So, if you look at the energetics wise, then E1 plus E2 is greater than E3. So, which means the reaction is favorable. The two dislocations of these Burgess vectors. So, basically this is B1 plus B2 giving rise to B3. So basically what we are saying is that when two Burgess vectors react with each other, sort of a chemical reaction like reaction, when two Burgess vectors, or you can say two dislocations, meet with each other, they give rise to another dislocation with a Burgess vector which is different, which is not the same. So, let us see what does it mean. So, we may have first plane, let us say we define one plane which is this plane. Okay. So, in this plane we had a dislocation which was, let us say, half, let us say O bar 1 1. Okay. And let us say this slip plane was bar 1 1 1, and if you take the dot product, they make 0. So, which means this was earlier moving in a plane which is bar 1 1 1 plane. Okay. Let us say we had another plane, intersecting plane. This another intersecting plane was something like this, and in this we had a dislocation which was, so this was B1. Okay. In this case B2. Okay. And then we had B1, this B1 was half 1 O bar 1, and let us say this plane was 1 bar 1 1. So, the dot product is again equal to 0. When they meet each other at the intersection point, so this is the, let us say, so let me just broaden this a little bit. So, this is the plane, let us say. At the intersection point, this is, let us say, the intersection, this is the intersection. At the intersection they move and they create this B3 which is half 1 bar 1 0, and this half 1 bar 1 0 does not lie in this plane, because 1 bar 1 1 dot 1 bar 1 0 is not equal to 0. Similarly, 1 bar 1 0 dot bar 1 1 1 is not equal to 0. So, which means the third dislocation which has been formed by these two dislocations does not have its Burgess vector lying in any of the original slip planes. Okay. So, which means this becomes immobile. So, what is this dislocation? So, this B3 is basically immobile in bar 1 1 1 or 1 bar 1 1, and this lies probably in a plane which is a different plane. This lies in a plane which is, let us say, this plane, and this plane could be 0 0 1 plane. So, if this is 0 0 1 plane, 0 0 1 is not a favorable slip plane, and for which, so 0 0 1 is not a favorable slip plane. So, which means it will have high CRSS. So, basically what we have done is, you have created two dislocations which were moving nicely in two different planes, but when they met each other they gave rise to another dislocation whose Burgess vectors is different. It does not lie in any of the original slip plane. The Burgess vector lies in another plane which is not a slip plane. So, as a result you increase the shear stress required to move the dislocation. So, essentially when you form this kind of dislocation, let us say you form this dislocation at this point. So, this is a, let us say this, we call it as a sessile dislocation, sessile or immobile dislocation. So, when you form this sessile dislocation at this point, all the dislocations which were moving behind it and all the dislocations which were moving here behind this, when they pile up, they create many of these. So, this cannot move. So, this has become immobile. So, which means all of these dislocations, they will get piled up. So, this will create sort of a, when they reach, they all will reach at this point. So, basically this will create a situation, will lead to dislocation pile up. So, as you have seen, on the intersections, when some vehicles go and if the vehicles are not able to move, then anything that comes from, so this is like the typical intersection. So, if you have vehicles coming from this direction, this direction, this direction, this direction, so these are the vehicles which are coming, and if there is a jam here, then all of these basically pile up. So, this is pile up, this is where you will have pile up, and this is where also we will have pile up. So, basically this is what is sessile dislocation, and all the dislocations which are moving from other directions, they get piled up because they do not, because the next dislocation cannot move, because the dislocation which is lying here at the intersection cannot move. So, as a result you have what we call as dislocation pile up. So, basically creation of a sessile dislocation can cause dislocation pile up. So, which means, so either dislocations move to other planes which are favorably oriented, or you also operate Frank-Reed sources. So, essentially all of these lead to increase in stress. So, basically when you have these dislocations piling up after one another, the dislocation pile up leads to creation of this. So, just to simplify this point, if you have one plane like this and you have another plane like this, let us say the intersection has, let us say this is the intersection, okay. So, this is the intersection. So, on both sides of this intersection, this is sessile dislocation, this is plane 1, this is plane 2, and the dislocations in both of these planes, in this plane and the dislocation in this plane, they all get piled up. So, basically you create a pile up of, and pile up of dislocations is going to lead to another thing. If they are all similar kind of dislocations, if they have similar signs, that means there will be repulsion between dislocation. So, let us say, so if you have multiple dislocations piling at a source, so this is let us say the blockage, okay, this is the blockage, and you have multiple dislocations piling up like this. This is what is the pile up, and you will have repulsion between the like dislocations. As a result, this will lead to increase in the stress that is required to cause the further deformation. So, basically the deformation requires motion of dislocation, and if you are basically obstructing the dislocations to move, so all you have done is basically you have created obstruction to move the dislocations further. So, it could be in the form of repulsion between like dislocations, it could be in the form of creation of new dislocations, whose Burgess vector is unfavorably oriented with respect to original planes, slip planes, because of dislocation pile up leading to blockage, and all of these lead to higher stress. So, that is why when we say tau is equal to tau naught into some constant A multiplied by square root of rho. So, basically this is the, let us say, base stress for a virgin material, one annealed material. So, this tau is essentially square root of rho, proportional to square root of rho. So, as the dislocation density goes up, the material becomes harder and harder to deform further, and this is what basically causes the material to become strong and less ductile. So, as material strain, as material is cold worked, it hardens, that is sigma y increases, but at the same time the ductility or percentage elongation decreases. So, basically it becomes hard and more and less ductile. So, basically what we are saying here is easy dislocation will mean lower stress, which means easy deformation, that is a soft material, soft metal, and difficult dislocation motion motion here will mean higher stress, it will mean difficult deformation and this results in a harder metal, harder or stronger metal. So, here large ductility, or you can say larger ductility, here it is smaller ductility. So, this is the first very simple method of making material stronger, just deform it more. So, this you can do simple experiment at home, you just take a wire and just try to bend it a few times back and forth, and you will see at the bend the material actually becomes stronger. This is something that you can see very clearly. You take this wire and you just bend it once, then release it, then bend it, then release it, then bend it, then release it, and you can see that at the bend it becomes strong and eventually it becomes so strong that you can't deform it further, it will break. So, it will actually become brittle. So, this is first method of making materials stronger, which is called as plastic deformation or work hardening or strain hardening. We will look at the other methods of making materials stronger in the next lecture. Thank you.